Okay, welcome back. So before we do anything new, I'd like to revisit yesterday's example and show that we can solve it by Lagrange multipliers in a different way. Instead of thinking of it as a two-variable problem with one constraint, we can also treat it as a three-variable problem with two constraints. So just for additional practice and to see what it looks like when you have more than one constraint, let's just do that quickly. And then we'll move on to talk about the theory behind the method. Okay, so again, the problem was like this. We have a certain ellipse, capital E, which is the intersection of the plane z equals 6 minus x minus 2y, and the right circular cylinder x squared plus y squared equals 1. And our task is to find the highest and lowest points on this ellipse. Okay, so what we did when we talked about this problem in the last video, let me call it method 1, was we took our function, our objective function, to be the height of the plane above the point xy. So in other words, you can picture it like this. You have the xy plane, and at a particular point, x comma y comma 0, in that plane, you can go up by z, which is by definition 6 minus x minus 2y. Okay, so in other words, we're taking the x and the y that are given to us. We have like a given value of x and a given value of y, and we just plug those into that expression, and that gives us the corresponding z value. Okay, but then by going up by that amount, we come to a certain point, and that point is always on that plane. So whatever that plane looks like, I didn't really draw an accurate picture of it, but whatever that plane looks like in space, we can treat it that way, as essentially the output of a certain function of x and y. And then, so that was our objective function. We wanted to maximize or minimize that because that's the height of that point. But the constraint is that it has to lie in that cylinder as well. Or in terms of x and y, the constraint was that the point xy lies on the unit circle. So in other words, we had g of xy, which we defined as x squared plus y squared, had to equal 1. So that was our constraint equation. Okay? So that was how we treated this as a two-variable problem. We had an objective function, which is a function of two variables, and then we had a constraint function, also a function of two variables, and we set that equal to 1. When you set that equal to 1, that gives the constraint equation. So it was a single constraint, one single constraint. Okay, well, now let's see how we can do it a different way. I'll call it method 2. Okay, so this time we're going to treat it as a three-variable problem, where the objective function, as a function of three variables, is just z. That's the height of a point. But now I'm going to have two constraints. The two constraints are the equation of the plane, so let me call that g1 of xyz. And that's...
Sorry, what was that?
Sorry about that. Alexa got a little overzealous. Yeah, so we had, what was it, 6 minus x minus 2y was equal to z, so we'll just subtract z. and set that equal to 0. See, that's equivalent to the constraint equation, which was that z had to equal 6 minus x minus 2y. All I've done is move the z over to the other side as a negative z, and that leaves a 0 on that side. So by writing it in that form, you see, we can express it in this form, g1 of xyz equals a constant. That constant is 0. So this is the constant that we would call C1 in the general theory. Okay, so that's our first constraint equation. The second constraint equation, let's have a second function, g2 of xyz, and that's going to be the function just x squared plus y squared. Notice that it happens to be a constant function with respect to z. We can think of it as involving like a 0z term, which of course does not have to be written. Okay, and that's going to be set equal to 1, which would be the constant c2. So you see that now we have one objective function. Always we have one scalar valued objective function, but now we have two constraint functions. And they're functions of 3 variables. Even this is a function of 3 variables. Right? Even g2 is a function of 3 variables. It just so happens to be constant with respect to one of the 3 variables, z. But you can still regard it as a function of 3 variables. And notice that the constraint equations consist of setting those two constraint functions equal to certain constants. In this case, 0 and 1, respectively. So that's a different way of treating the problem, but let's go through the solution to illustrate how the Lagrange multiplier method works when you have more than one constraint. Okay, the idea is that step 1 is to secure the existence, prove the existence of the requested max or min point, or points. We don't know how many max or min points there will be, because in general, if the function has a maximum value that it takes on, subject to those constraints, then it may take on that maximum value at many different points. So we don't know how many points there will be, but we just need to prove that there's at least one point at which the maximum is taken. Okay, and there's also at least one point at which the minimum is taken. Because we're looking for the max height of a point on that ellipse, and we're looking for the minimum height of a point on the ellipse. So we have to know that those exist. Okay. So the idea is to use, of course, the extreme value theorem. We're considering the function f restricted to a certain constraint set, capital S. The constraint set is just the set of all points x, y, z in space that satisfy the two constraint equations. That's the equation of the plane, and this is the equation of that right circular cylinder. So I put the conjunction sign between them just to remind you that that's what it is. It's a logical conjunction, or in other words, it's an intersection between two sets, one of which is a plane and the other of which is a right circular cylinder. Okay, so that's our constraint set. So what can we say about that constraint set? All right, well, in a video that I'll post very shortly, okay, the reason I haven't posted this video yet is, although it's been recorded already, it's just that I've been having certain technical problems with the apps that I've been using. This is partly why I have not posted very much lately. So I have to basically salvage the video from that by re-recording it. I haven't gotten around to that yet, but I'll do it. I'll do it soon. But anyway, in this other video to be posted shortly, I give a complete proof that when you have a continuous function like this, and you set it equal to a constant, creating this type of an equation, the resulting set is closed. The set of points that satisfy that condition is a closed set. Okay, and the same applies to this. I have a continuous function here. I'm setting that equal to a constant. So that set is also closed, that solution set. And then the intersection is also closed. Because in general, intersections of closed sets are always closed. Arbitrary intersections. Remember from a long time ago that arbitrary unions of open sets are open, and also arbitrary intersections of closed sets are closed. So if I take two closed sets and intersect them, you get a closed set. So that proves that S is closed. Okay, and then the only other thing to show is that it's bounded. And that's also quite easy to do, just by showing that each variable is bounded. You see, having to satisfy this equation involves forcing x to be between -1 and 1, and also forcing y to be between -1 and 1. Because obviously, no point x comma y comma z that has this property, that the sum of these two squares equals 1, you can't have the x be something like -2. Because the square of that is already 4. It's already bigger than 1. And y squared is non-negative, so it can't compensate. So that shows that the x and y coordinates are bounded. Okay? And then as for the z coordinate, that also has to be bounded just from this equation here. You can see that by expressing z in terms of x and y, you see that like the absolute value of z can be bounded by the triangle inequality less than or equal to... Hold on, let me just make a little room here. So less than or equal to like 6 plus absolute x plus 2 times absolute y, and those are both bounded by 1. Like the absolute value of x is bounded by 1, and the absolute value of y is also bounded by 1. So you see that the z-coordinate is also bounded between -9 and 9, at worst. Right, so this condition here involves bounds on absolute x and also absolute y, and then absolute z is also bounded. So in fact, the entire set S is within like an axial box, where in the x and y directions the edges are of length 1, and then in the z direction... sorry, that's a little wrong, because it's 1 in each direction. So I should have said dimensions 2 by 2 by 18, right, in the z direction. So this is not drawn to scale, obviously, but the point is that the entire set S is within that box, so it's certainly bounded. Right, so I'm saying like from height 0, you go up by 9 units and down by 9 units. And that gives the complete range for z. Or going this way by 1 unit and that way by 1 unit gives the complete range for x. Okay, good. So that shows that S is bounded. And because it's both closed and bounded, it's compact. And of course the function f is obviously continuous. This function here is obviously continuous with respect to the point x, y, z, even though it doesn't involve x or y. See, this is actually a famous function. We talked about this in class like last semester. It's pi 3 of x, y, z. It's the third projection. So you're projecting the point x, y, z onto just the z axis. But remember that projection functions are always continuous. So this is continuous function everywhere. In fact, its region of continuity is the entire xyz space. So let me be even more precise and say that. It's continuous on the entire R3. Okay, so certainly because S is compact and the function f is continuous on that set, the extreme value theorem applies. And the existence is thereby secured by EVT. So that's step 1. Okay, we have to be sure that that there are. It's only the points in the set S that satisfy both constraint equations that we are concerned with whatsoever. Any point outside of S is totally irrelevant to the slides. You'll see why. Look at the function g1. See, x has a coefficient of -1, y has a coefficient of -2, and z also has a coefficient of -1. It's only because that function is a first degree function that the gradient is coming out constant. A first degree function has a constant gradient, constant derivative. So that's not a general feature, it's just a particular kind of coincidence of the fact that we have a plane here. One of the surfaces that we're intersecting is a plane, which has a first degree equation, the max and the min that we want, that they exist. Okay, step 2 is going to be to find them. By doing the following thing. We're going to take the Lagrange condition conjoined with the constraint equations. That's going to give us one system we're going to solve. That's one source of candidate points. The other source of candidate points is the degeneracy condition, conjoined with, again, the constraint equations. Okay, so I wasn't quite clear on this in the last video when we talked about method 1, because I just basically said, well, you look at the Lagrange condition and then you look at the degeneracy condition. But you have to look at them together with the constraint equations, because it's only the points that satisfy the constraint equations that we care about. In other words, so in both cases we have to take the conjunction of the relevant condition, either the Lagrange condition or the degeneracy condition, but you have to take the conjunction of that condition with your constraint equations. And that gives you two classes of candidate points. And the theorem is going to say that the max that exists, the max that you already know exists, must occur among those candidate points somewhere. And also the minimum, if it exists at all, if you know it exists, then you will find it among those candidate points. How do you find it? Well, you just plug in all the candidate points, assuming you have only a finite number. And you see which one gives, the function its greatest value, and which one, or ones, give the function its least possible value. Okay, so let's look. The Lagrange condition for us goes like this. It's the gradient of f is going to be set equal to a linear combination of the gradient of g and, or g1, let's say. Okay, so I'll call it lambda 1 then. I'll use the same notation that I used in yesterday's video. So instead of calling the Lagrange multipliers lambda and mu, which I normally do in practice, but I'll just call them lambda 1 and lambda 2. Okay, so we're going to try to find all the solutions of this equation, but we also need the constraint equations. G1 is going to set equal to C1, G2 will set equal to C2. So basically that system of equations is what we're looking to solve. Okay. Now as for the degeneracy, yesterday I told you that when there's only one constraint, when you have only one constraint of the form g of x equals a constant, then the degeneracy condition can be phrased in this way. Just the gradient of that g you set equal to 0, the 0 vector. But here we have two constraints, and I didn't say in yesterday's video what the corresponding equation actually looks like. So I'll say it now. Okay, the idea is just that the two gradients okay, let me just do it in a very general form, and then I'll do it in a more specific form that's useful for calculations. Okay, the most general way to write it is this. It's that the determinant of G prime transpose times G prime is 0. And then, of course, you still want the constraint equations with that. So again, it's like a system of equations. Okay, now here there's a new notation that I haven't used, at least not in this video, up to now. That is vector g. But of course it should be clear what I mean by that. What I mean by the vector g is just the function whose two component functions are g1 and g2. So it's a vector-valued function. And it has a Jacobean derivative matrix, g prime. You have to take that matrix, multiply it by its own transpose, and then take the determinant. Okay, that product here, this product right here, will be square. Okay. In fact, you can see that both of these are functions of three variables, g1 and g2. So the function g maps 3 space to 2 space, because the outputs of that function have two components, g1 of the point and g2 of the point. So you're going from 3 space into 2 space. That means that g prime is of size 2 by 3. Remember that it's the codomain dimension first by the domain dimension. So if the map goes from 3 space to 2 space, then the size of the derivative matrix is 2 by 3. And then the transpose of that will be 3 by 2. So you see that when you take the product, first of all, the product is well defined because these 2's match up. And then the size of the product is 3 by 3. So you're taking the determinant of that 3 by 3 matrix and setting it equal to 0. That's a very general way of stating the condition. Okay, but there's a more specific way stating the condition that's also very useful in practice, which I'll get to in a few minutes. Okay, well, let's take a look at the Lagrange condition first. So let's see, we're going to compute the gradient of f. That's very easy. F is a very simple function. It's just the function z. So its gradient is just the vector 0, 0, 1. But this is the df dx. It's the same as dz dx. This is df dy. This is df dz. But since the function is just z, that's dz dz, or 1. Okay, so that's the gradient of f. It's pretty easy to get. Okay. Back of couple in this system here. The Lagrange condition, which is this equation when you have two constraints. And it will be a very similar equation if you have k constraints. Okay. But then you also have to take the constraint equations you were given as part of that system. So that system as a whole, I'm going to call the Lagrange system. And let me call the other system as a whole, including, again, the constraint equations that we were given. I'll call that the Degeneracy System. All right, so it still remains to look at that. The Degeneracy condition is, it's just saying that the determinant of the Gramian, I have this matrix G prime, which is like my A. Then I have its transpose. So I'm basically taking the Gramian matrix and then taking its determinant. And setting the determinant equal to 0 is the same as saying that the original matrix A does not have linearly independent columns. Because if it did have linearly independent columns, then the determinant would be non-zero. The Gramian matrix would be invertible. And therefore its determinant would be non-zero. So by setting the determinant equal to 0, what I'm saying is the Gramian is not invertible. Therefore, the columns of A have to be dependent. The columns of A have to be dependent. Also, the rows of A have to be dependent, because that's equivalent as well. The degeneracy condition. The degeneracy condition for us, which I phrased here in terms of the Gramian, But we can also rephrase it by just saying that those gradients, these two gradients here, are dependent, linearly dependent. What about the gradient of G1? So let's remember that if we partially differentiate with respect to x, we're going to get -1. Partially differentiate with respect to y, we're going to get -2. And then with respect to z, it's also -1. So if you go... In general problems, you're not going to get constant gradients. You're going to get gradients that depend on x, y, and z. Depend on the variables in question. Okay, G2, if you differentiate with respect to x, you get 2x. With respect to y, you get 2y. And with respect to z, you get 0. Because remember, the function is just this. It doesn't involve z. Okay, so the Lagrange condition becomes the following thing. We have 0, 0, 1 equals lambda 1 times this plus lambda 2 times this. And we can split that up into three scalar equations. Okay, it looks like that. And then don't forget that we also have our constraint equations. Well, okay, let me write them in the correct order. First one was that, and the second one is this. So we're basically looking to solve this system. Notice that that's a system of 5 equations in 5 unknowns. The 5 unknowns are x, y, z, lambda 1, and lambda 2. Okay, now something quite nice is that lambda 1 has a value that's basically immediately known to us. Its value is just given to be -1 by one of the equations. So we can update our system by replacing lambda 1 with -1. So that gives us these 4 equations in 4 unknowns. Okay, now notice that lambda 2 can't be 0. Because if lambda 2 were 0, then you would have this inconsistent equation. This would read 0 equals 1, which is obviously false. So lambda 2 cannot have the value 0. And therefore, it's acceptable to divide through by lambda 2. Okay, and so what we can do is we can like subtract 1 from that top equation and then divide by 2 lambda 2. And express x in terms of lambda 2 like that. We can also do similarly with the second equation, like subtract 2. Well, you can just divide out a 2. And subtract 1. And that solves for y, like that. So you see that by putting the 2 back on this side, instead of putting it down here, then, oops. Okay, now you see that the 2 expressions are equal. So we conclude that y must equal 2x. And then we can go and solve basically the same way we did yesterday by plugging that condition into the circle, the equation of the circle. We find that x has to equal plus or minus root 5 over 5, and y has to be twice that. So again, the 2 plus or minus signs are correlated here. They have to be the same sign. And then the z can be solved from the last remaining equation here, and once x and y are known. So we already looked at that yesterday. We found that basically z was 6 minus or plus radical 5. Notice the minus plus sign is used only when there's already a plus minus. There's already this plus minus, which occurs twice. And then we use the minus plus to show that that one is oppositely correlated with the plus minus. So in the top case, these two are pluses and this one is a minus. And in the bottom case, these two are minuses while this one is a plus. Okay, but that's the idea behind these plus or minus versus minus plus signs. It's a useful notation. Okay, so that gives us candidate points. That's all the candidate points there are that come from that system. That system being the Lagrange system. Let me refer to it that way. By the Lagrange system, this back here, the condition as solutions of the Lagrange system. Okay, and so since there's only two candidate points, and we already know that there must exist a maximum by the extreme value theorem, and also there must exist a minimum, also by the extreme value theorem. So whichever of the two candidate points gives the higher z value, which is 6 plus root 5, must be the point where the maximum is achieved, and it's unique. And the point that gives the lower z value, 6 minus root 5, is the unique minimum. Okay, so that shows how we can solve the problem as a three variable problem with two constraints. But either way is fine. Okay, so anyway, that should give a pretty good flavor for how these things work out. Okay, so I said that I was going to tell you a way to think of the degeneracy equation, or the degeneracy condition, in a more computational form. Because that determinant, that 3 by 3 determinant, can be difficult to calculate. Because it's not a constant matrix that you're taking the determinant of. It's like a matrix whose entries are functions of x, y, and z. So computing a 3 by 3 determinant where all the entries are functions of x, y, and z can be a pretty intense algebraic exercise. But we can think of it a different way. It's going to turn out, I'm going to show you why this is true a little later, but it basically turns out that when you have a matrix A, let's say size D by E, so A transpose times A is called the Gramian of A. It's named after Graham. That's the same Graham as in Graham-Schmidt, the Graham-Schmidt process. Anyway, so that product is called the Gramian. And that's obviously square, because you have like D by E, and then this is E by D. So this is an E by E square matrix. Okay, and the determinant of the Gramian, it turns out, is non-zero if and only if the columns of A are linearly independent. And that happens, of course, we know already from earlier in the semester, or earlier in the year, I should say. But we know that that happens if and only if the rank of A is full. Full means, maximal, as large as it can be. Remember that the rank is bounded in general by the smaller of the two dimensions. So when the rank has that value, when the rank is equal to that bound, then we say that the rank is full. It's a matrix of full rank. And that happens if and only if its columns are linearly independent. Okay. Also, remember, determinant being non-zero is itself equivalent. So this is itself equivalent to the Gramian matrix being invertible. So we have an interesting theorem here. This is a nice, very useful theorem of linear algebra, which we'll talk about a little bit later on. Okay, but you see that that's really all another equivalent condition to these is that the rows are independent. Okay, and of course, if you negate everything in these equivalences, if I take the denials or negations of all of these statements, this would say like non-invertible. This would say is equal to 0. This would say dependent. Right? This would say not full. And this would also say dependent. Anyway, so then the rows have to be dependent. Okay, now what are the rows? The non-degenerate, so we can rephrase because of this theory of the Gramian matrix, which we'll get to soon. And if you remember what the Jacobean derivative looks like, the rows are just the derivatives of the component functions. So if the function g has components, g1, g2, and so on, then the Jacobean derivative matrix is composed out of the following rows. You take the derivative of the first component function, so g1 prime. That's a row matrix. The reason it's a row matrix is because g1 goes from D space, or some subset thereof, into the reals. And so its derivative is of size 1 by D. In other words, it's a row. And that's actually the first row of G prime. Okay, and this goes on and on like that. Okay, so, and if I take the transpose, then that just takes all these things and transposes them. So for example, here I have G1 prime transpose as a column. Then I'll have G2 prime transpose as a column. Now we have a name for those transposes. The transpose of the derivative is called the gradient. So that first column would be the gradient of G1, then the gradient of G2. So you see that those are going to have to be linearly dependent. Those gradients are going to have to be linearly dependent if this matrix here is not of full rank. See, if this is not of full rank, it follows that this is not of full rank either. Why? Well, the rank of a matrix is equal to the rank of its transpose, as we proved in class a long time ago. So between G prime and G prime transpose, they have exactly the same rank. Therefore, one of them is of full rank only if the other one is, if and only if. And one of them is not of full rank if and only if the other one is not of full rank. Well, being not of full rank means that you have linearly dependent columns. Okay, so in our case, we're going to conclude that here, and because of these facts about the Jacobean derivative, the relationship between the Jacobean derivative and the gradients of the components, all of these things come together to show that the linear dependence of those gradients, in other words, the linear dependence of these columns, is equivalent to the degeneracy condition. Degeneracy condition as saying that the gradient of G1 and the gradient of G2 are like parallel. In other words, linearly dependent. Yeah, we can describe it as being parallel because it's just two vectors. Linear dependence between two vectors just means that one of them is a multiple of the other, or maybe they're both 0. But in either case, we describe that as saying that they're parallel. Yeah, let me just take a moment to explain that. See, if I have just two vectors v and w, linear dependence means that there exists a linear combination of the two, which is equal to 0. But the two coefficients are not both 0. Like, they're non-trivial. In other words, not both 0. So, yeah, that's what dependence means. means that there's a non-trivial linear combination of the two that's equal to the 0 vector. Okay? But then you see that we can rearrange the equation. Like if A is not 0, one of the two is not 0. They're not both 0. So let's say A is not 0. Well, if A is not 0, then we can put the BW term on the other side and then divide by A. And that expresses V as a multiple of W. Right? If B is the non-zero one, then we can do likewise. We can express W in terms of V. But you see that one of them can be expressed as a multiple of the other. So in either case, they're parallel. We can say it that way. And parallelism of vectors is very easy to check, because parallelism of vectors just is equivalent to proportionality. Let me use this symbol for proportionality. Physicists tend to use that symbol. It's kind of like an infinity sign, but it's not closed. Okay, what does proportionality mean? It just means that the components of V have to be multiplied by the same scalar. Take every component of V and multiply it by the exact same scalar to produce the components of W. Or vice versa. Take all the components of W and multiply them by the same scalar, and that will give you all the components of V, corresponding components. So that's easy thing to check for. So when you have two constraints, this is a good way to think of the degeneracy condition. It's totally equivalent to the general form of it, as I explained. Now again, for just two vectors, linear dependence is totally equivalent to parallelism, which is also equivalent to proportionality. And that's an easy thing to check for. Okay, well anyway, let's see how it works out in our case. We know what the two gradients are. This gradient here turned out to be like -1, -2, -1. And then the other gradient was 2x, 2y, 0. Okay. Now don't forget that there's also the constraint equations. They have to be considered as well. We have to consider with this the two constraint equations themselves. We have to put all of those together as a system. And that's our degeneracy system. Okay, so let's see how it goes. We can separate. Actually, it's actually quite easy in this case to analyze, just because we're kind of lucky that there's a 0 here. Because you see, no scalar will do this for you. If I multiply it by a scalar, any scalar that I put here, let's say lambda, will take this 0, and it cannot produce a -1 in that corresponding slot. Because 0 times lambda is always 0. Never equal to -1. So you can't use that direction. But potentially you could use this direction. The thing is, in this direction there's only one constant that could work as a multiplier, which is 0 itself. Because -1 times 0 does indeed give you that 0. Okay? So the only proportionality constant that's even a candidate is 0. And you see what happens if I multiply this first component by that proportionality constant. I get 0. That forces x to be 0. And if I multiply that second component by the same proportionality constant, 0, then it forces y to be 0. Okay? Now once I know x and y are both 0, this constraint tells me that z has to be 6. The thing is that single point that we just found does not satisfy the last constraint. This last constraint is not satisfied by that point because, the sum of the squares of x and y is not equal to 1. It's equal to 0 for that point. So in fact, you see that there are no solutions. Okay, what I'm saying is that this combination here satisfies the proportionality statement. Gradient of g1 is parallel to gradient of g2, and it satisfies the first constraint, g1 equals c1. But it doesn't satisfy the second constraint. g2 is not equal to c2. In other words, this equation here doesn't come out true for that point. So in fact, there's no solutions. Overall, as a system, there are no solutions of the degeneracy system. Okay, so this leaves us with only the candidate points that we in practice. And now I want to just start taking a look at the theory. So I'm going to state the theorem, and then we're going to start looking at the proof. Okay, and I'll probably break that up. I'll break off the proof into a separate video of its own. But let's at least state the theorem. Okay, so it's going to go like this. Let f be a function from some open region in D space, and that's into the reals, and we're going to assume it's C1. It has to be at least C1 for the proof methods to apply. So the method of proof we're going to be using is we're going to apply the implicit function theorem. The implicit function theorem is going to be the main sort of engine that makes the proof work. But the implicit function theorem applies only in the C1 context. So for that reason, I need my objective function and my constraint functions to be C1. Okay, and let G be a vector-valued function from an open subregion of D space. Let's call it capital V, into K space, also a C1 function, in the sense that each component of G is C1. So each component, like G has component functions G1, G2 to GK, and each GJ, let's say, goes from V into the reals and is C1 for all J from 1 to K. All right, here I'm assuming that K is at least 1, but at most D, and you're going to see why that's necessary. If K were greater than D, if we had more than D constraints, in other words, so I should remind you that K is the number of constraints. Let me actually explicitly write that. K is the number of distinct constraints in the problem. If you have more than D constraints, but you only have D variables in your problem, then you can't reasonably expect any solutions at all. The constraint set is most likely to be empty. By chance, it could be non-empty, because the functions G1, G2 could be sort of dependent on each other. They could be specially chosen so that there are solutions. But in general, if you choose those component functions independently of each other, it's very unlikely that there will be any points in that constraint set at all. So then you'll be restricting f to the empty set. And that's just the empty function. It's not you can't study that with calculus. Okay, so to avoid the empty function, to avoid a function with an empty domain, we have to make sure that the constraint set is not the empty set. And for that reason, we need to restrict K to be at most D. The number of constraints is at most the number of variables. Okay, and we also need to assume something else, which is that U and V intersect in a non-empty set. I'm going to call that set capital W, and I'm going to assume it's not the empty set. Okay, this is because, if U is over here and V is over here, then the only points that satisfy the constraint equation, g of x equals c, are going to be points in here. So the whole constraint set is going to be in there. But I can't restrict the function to that S because the domain of the function is here. So you see that S has to be within the domain to restrict F to that set. Okay, so we need U and V to overlap. Otherwise, nothing will make sense. So I'm going to call their overlap W. And notice that W is open as well, because although arbitrary intersections of open sets are not necessarily open, but finite intersections of open sets are open. So we can say W is open as a finite intersection. You can't take an arbitrary collection of open sets and intersect them. You won't necessarily get an open set when you do that. But you can certainly take a finite collection of open sets and intersect them. So because W is a finite intersection, just two open sets, then it is also an open set. And we're assuming that it's not the empty set. That's built in as a hypothesis. Okay, so now let S, which is the constraint set, be defined as follows. We take all points x in W. So why in W? Well, that way, those points are both in the domain of the function f and in the domain of the function g. So there are no domain problems at all. Okay? So you take all x in W such that g of x is equal to c. And this is where c has to be in the range of g restricted to W, so that there are some x's in W that satisfy. Okay, sorry, the app is new and confusing. So here we go. Okay, so yeah, I need to make sure that C is in the range of G restricted to W, because I want to make sure that there's at least one value of x in W that satisfies this. At least one value of x in the set W such that G takes the value C at that point x. To make sure that that's true, that at least one x lies in W and satisfies G of x equals C, I need to make sure that C is the value of the function G at some point in W. So if I restrict G to the set W, look at the values that G takes on that set, which is this range. I want to make sure that C is one of those values. Okay. So again, all of these conditions, all of these technical conditions are designed to make sure that the set S is non-empty. The set S has to be a non-empty set. And I'll even say that explicitly, so that S is not the empty set. Okay, and then we're going to say that if the function f restricted to the set S has a global maximum point P, right, in the set S, or a global minimum point, let's say Q in S, or the min, then one may simply not exist, and then the candidate, then P and or Q, whichever we know to exist, sort of in advance. And what I mean by that is you have to know that there is a maximum point from some other source. You have to sort of know from some independent source, like the extreme value theorem, that the maximum exists. Provided that you know that, provided that that is known, then those points are among the solutions of either the Lagrange system. And here's what that looks like. It's going to be gradient of f is a linear combination of the gradients of the g sub j's. And there are k of those, g1, g2 through gk. Those are the component functions of the vector-valued function g. And remember that in the Lagrange system, we also include the constraint equations. So I'll write that in vector form, like this. So this is a system of d plus k variables, which are x1 through xd, and then also lambda 1 through lambda k. Oh, I'm sorry. I said that a little wrong. It should say d plus k equations in those variables. Right? Well, it's obvious that those are the variables, because, the point x that appears is just a shorthand for those d variables, and then the lambdas also appear. Lambda 1 through lambda k make an appearance in this equation here. So those are all the variables that appear. They're exactly d plus k, distinct variables. But how do I know that there's d plus k equations? And why is that important? All right, well, first let's just count the equations, and then we'll see how we know, or why that's important. Okay, this itself is this is k equations here. Right, because the vector-valued function g is just a shorthand for these k components. And if you read those equations one component at a time, it's going to give you k scalar equations, k sort of scalar-valued equations. Okay. I claim that this is d scalar-valued equations here, or sort of packaged into a vector form. Reason is because these gradients are d-dimensional. These gradients are in d space. Right? Remember that the gradient is like df dx1 up to df dxd. So it's a d-dimensional vector. So if you just separate out all the d components, write them each as an independent equation, it's going to give you d equations. So what you have in total is d equations and then k additional equations. So you have exactly d plus k equations, and you have d plus k variables as well. Okay, the importance of that is that we expect there to be just a finite number of solutions. Now that doesn't have to happen of necessity. It does not have to happen. You could have an infinite number of solutions, but at least you have a good chance of having just a finite number of solutions. And the reason is because of the implicit function theorem. Okay, well, actually, just very informally, let's just think about this very informally. We want to have exactly enough conditions on our variables to nail down their values exactly, with no degrees of freedom. You see, if we had too few equations, like let's say we had d plus k minus 1 equations in d plus k variables, then we would expect to have 1 degree of freedom. That would be a continuous degree of freedom. Some continuous parameter that we could vary in a continuous fashion and get a whole family of solutions, a whole parameterized family. Or if we had, let's say, d plus k minus 2 equations, we would expect to have 2 independent parameters that we could vary continuously. But with exactly the same number of equations as variables, we expect to have no parameters, which means that you can still have many solutions, but hopefully you have a finite number, and at worst maybe countably infinitely many. So that gives you a better chance of actually finding the candidate points. Okay, because if we had a vastly infinite family of candidate points, that would not be useful. Since in the end you have to plug all your candidate points into the objective function f to have any chance of figuring out which one is the max or which ones are the max, and which ones are the min. Okay, so that's the Lagrange system. Let me just erase a few things here. Okay, so remember I said either the Lagrange system, and now following up on that, or the degeneracy system, okay, and the degeneracy system, the degeneracy system, if P is the global maximum of F on that constraint set S, and we know in advance that it exists, we can independently establish the existence of P, then P will be one of those candidate points. It will be among the solution points of either the Lagrange system, or possibly, if Q is the global minimum of F on the constraint set S, and if we know in advance that that exists. By the way, there may be many points P that work, because there may be many points at which the function is tied for its maximum height. And there also may be many points Q where the function F is tied for minimum on the set S. But the point is, any one of those P's, any one of the points that give a global maximum of F on S, will be among your candidate points, among the solutions of the Lagrange system or the degeneracy system. And then all of the points Q that give the minimum value of F on S also will be among the solutions of the Lagrange system or the solutions of the degeneracy system. Okay, so that's the Lagrange theorem, and it yields this very powerful technique. You just find all the solutions of both systems, and you plug all of those candidate points into the function f, and see, But of course, you have to establish the existence of the relevant min or max in advance, usually by appealing to the extreme value theorem. Now, it doesn't have to be the extreme value theorem. It could be one of those other theorems that we studied that deal with the existence of maxima and minima. So you'll remember that there was what I called the max VT. Know the existence of the max that you find by solving the Lagrange system or solving the degenerate. We can write something like this. In general, the determinant of G prime transpose of x times G prime of x equals 0, and then of course we have the constraints, which we can write in vector form like that. Okay, so that's what the theorem says, the degeneracy system. And similarly, let me just remind you about this. There were basically 3 existence theorems that we could appeal to. And there are various other smaller, more minor ones. But the main ones, the main existence theorems for extrema, were the extreme value theorem, which is by far the best, easiest to use, and most powerful. But it does require the set to be compact. Okay? If you don't have a compact set, S, if your set S is not compact, then you could attempt to use either the max VT, the maximum value theorem, or the minimum value theorem. Okay, and you'll remember how that goes is that if we have a set S that's closed, but unbounded, say I have some set S that's kind of unbounded in some directions, but closed. So the idea is that if I can find a compact subset, K, of S, such that the function achieves a value here in this set less than or equal to all of its values outside. So the value of the function at some point in k, let's call this point p. So f of p is going to be like less than or equal to f on the entire set s minus k. Right? If you can find that, then you know that the minimum must exist, and in fact it must be achieved somewhere within k. Because you can minimize f on the set k, since k is compact. But then that minimum is actually global minimum on all of s, because the values of the function out here are too big to be the minimum. That would be like the min vt. And if you reverse the inequality, then you'll get the max vt. So those are some existence theorems that you can appeal to try to secure the existence of the relevant extremum, which you have to do in advance. Otherwise, the Lagrange theorem doesn't help you. You see, if you use a system, those candidate points are totally meaningless. They don't give you the max. Like, the max points are not among those solution points because they simply don't exist in the first place. And similarly, the minimum points are not going to be among those candidate points because they just don't exist in the first place. It's only if those points exist that they have to be among those candidate points. So the existence has to be established prior to using the Lagrange method, and you have to do that independently of the Lagrange method, basically by appealing to a pure existence theorem. Okay, well, with that said, I'm going to break off the video here, and in the next one I'll do the proof of the Lagrange theorem. I'll lay out the complete proof. Okay, see you then.